time we are going to look at the unique soils called volcanic ash soils. Some people call them andosols, others call them andisols, but actually they are volcanic soils. These are soils which are formed after the volcanic eruption has occurred, then the igneous rocks are weathered, then you come up with these materials. Some of these things show you that there was rapid cooling and rapid whatever, then these materials are present. But we are going to show you how these things came in and what their characteristics are. Actually, these soils are very unique to this part of the world, or the country. Uganda has predominantly feral soils. Most of our soils are red soils, what we call the feral characteristics. And this is what I'm going to discuss with you, so that you know why we are here. But unfortunately, these soils have been misused, as we have heard from the previous discussions. Population has increased, there is inappropriate land use planning. You find that people are building houses where there should be agricultural activities, and that's unfortunate. But having said that, let me take you to the story of andosols. Those of you who are with me in Kirembe, at the upstream side of Kirembe, I talked about the journey of soils, the journey of rocks, igneous rocks, most of rocks and sedimentary rocks. And I talked about three types of rocks, igneous, sedimentary, and but I told you the journey from Twaha to the mantle to the crust, and then what happens when the volcanicity. I will not repeat that. But once the volcanic eruption has happened, we have certain landforms that come up. For example, the top here we have quite a number of shield volcanoes. Shield volcanoes mean that when the magma came out of the vent, it's traveled a long distance, showing gently resulting into gently sloping landforms. Those are what we call shield volcanoes. They are very prominent here. But in some places we have so-called cones. But these cones have come in such a way that whenever there was an explosion in a vent, the ash materials would splash up in there and then come back and cool rapidly, forming cone materials and crater lakes. So most of these craters, where you see a crater lake, means that at one time there was an volcanic activity there. There was an explosion and materials went out. So everywhere you see a crater lake means that there was a pipe down there where materials came out, and then water came, after cooling, water came and filled that part, and that's why they are very deep, because these are very deep pipes that go up to sometimes the core. So, where we are here, in Fort Portal, we are seated on what we call volcanic soils. Some people call them andisols, take it not carefully. Others call them andosols. Others call them volcanic ash soils. Their volcanic soils are unique in that their chemical and mineralogical composition is marked by abundance of easily weatherable minerals. Olivines, the amphiboles, I'll talk about that later on. These are easily weatherable, means that they can easily break down to release the nutrients. That's why you really missed to do read and the morphology. So they have those amphiboles, which are very common in Africa. They have high P fixation. These are things you may learn from soil chemistry. They have what we call immogoles. These are also textosilicates made out of silicon and iron and oxygen that form the clay materials that we see here. Then we have a lot of what we call ferrhydrate materials. These are hydrous iron oxide materials that are very common with volcanic ash soils. Ferrhydrates, these are, how would you call it? They are hydrous iron oxide. Hydrated iron oxide, yeah. So a lot of iron in them. I'll go through here. Andosol formation essentially depends on rapid chemical weathering of porous, permeable, fine-grained parent material containing volcanic glass. These are the volcanic ash materials, volcanic glass. We call it volcanic glass. In the presence of organic matter. So once there is a lot of organic matter, and these materials are there, then you have your volcanic andosols forming very rapidly. These are volcanic ash materials. Abattoir call them evikencha. They use them for building. But they normally occur in high terrain positions. Gentle sloping mountains and hills. They are very common here, these landforms. Sometimes they contain what we call volcanic glass, ferromagnesium minerals, which Dr. Rupert was talking about yesterday. These are minerals which are there in the soil materials, and things like olivine. I don't know whether people know olivine, pyroxenes. This is now chemistry. Amphiboles, feldspars, and quartz. These are materials which are here. Dr. Rupert talked about them yesterday, that's why I don't want to repeat them. But characteristic of these undersoils is that they have high organic matter content. That's why if you move around here, you see most of our soils in Fort are black in color. They are volcanic and they have a lot of organic matter. That's why they are very productive. They have what we call high aggregate stability. I hope you remember that from my soil physics classes. Very high aggregate stability. They are highly permeable to water. They have very low bulk density, so they can retain a lot, but they have low bulk density. I hope you know the implications of low. If a soil has high bulk density, it means that it's very hard. Water cannot go there, and eventually what you see is erosion. But erosion is minimal here because of the low bulk density and the high organic matter content. The organic matter, you know, organic matter is like a sponge. You remember that? Actually, 1 gram of organic matter can absorb up to 20 grams or milliliters of water. You understand that? So that means that when it rains, the organic matter soaks this water, it keeps it, and releases it slowly to the surrounding environment. So and that's how undersoils become very productive, because they retain they have a high organic matter content which absorbs a lot of water, which they release slowly to the environment. And for that matter, they have high moisture content. They also have high cation exchange capacity because of the high organic matter content. But what soil physicists have told us is that it is very difficult to disperse soil materials of organic undersoils. When you do how do they call it? Mechanical analysis of soils, you put sodium metahexaphosphate, you know that material, to separate the sand, silt, and clay. But for undersoils, it's very difficult to separate those materials because of their nature. So this always gives problems in making a texture analysis, and interpreting data from organic undersoils becomes a challenge because of that problem. And the pH values of undersoils is funny, by the way. If you have allophane and immogolite, those materials I talked about, these are silicates. If they are predominant, then the pH is normally what? Is normally more than 5. And if you have those hydrous oxides, iron oxides, then the pH is normally very low, it's less than 5. So for you to be able to appreciate the pH levels when you get them here, you have to do a mineralogical analysis. Where you have a lot of alophanes and immogolates, the pH is above 5, which is common here where we are. Where you have ferrohydrates, then you have pH very low, just like that one of ferrous soils. And that's a challenge in their management. But sometimes we have aluminium here occurring in very toxic, it occurs to very toxic levels, it becomes toxic to plants because of the low pH, especially when you have iron hydrous oxides. The other challenge of undersoils is that they have high affinity for phosphorus through what we call chemisoption. So these amorphous materials like immogolates and alophanes, they absorb a lot of P. So most of the phosphorus here is actually fixed, just like it is fixed in oxysols. So because they have high organic matter content, they are very fertile soils. So they have a high potential for agricultural production. That's why if you come here, you see a lot of crops being grown, as I'm going to show you. Actually, our soils have very high natural fertility. They have very high natural fertility. The only problem is pea fixation, which we can also manage. How do you manage pea fixation? You can inoculate the soils with what we call pea solubilizing bacteria. Those who do, there's a lady here who told me that she's interested in microbiology. Are you the one? Yes. I hope you understand and appreciate what I'm talking about. We have bacteria which can solubilize this pea so that it becomes available in the soil solution and become available to plants. But you can also apply lime to manipulate the pH so that the pea becomes available. We can use silica, we can use organic materials. And how do organic materials help us to get pea available? The organic materials have the capacity to block the pea sorption sites. This is chemistry. I hope you know these things. Do you really remember these things? They are what we call sorption sites on soil materials, on soil clay materials. So when you introduce a lot of organic matter, we have organic pea, which is in the organic materials, which is initially taken up by the pea sorption sites, so that they are no longer available to take up the pea that is natural in the soil. So once you block those pea sorption sites, then whatever pea that is remaining in the soil solution is available for crop uptake. I don't know whether we understand each other. So that's how you can manage pea and pea fixing soils, like feral soils and the soils. I don't know if you remember that kind of chemistry. This is soil chemistry. And I was telling my colleagues here that if you don't know soil chemistry, then you are not a soil scientist. Because the soil is a chemical factory. There are many reactions going on there. So if you don't, unless you understand the chemistry there, you cannot appreciate what we are talking about. But that is the truth. Because these things have been researched over and over again. They have been researched. So if you don't believe in me, then I don't know whom you will believe. Because these soils have a low bulk density and high organic matter content, they are very easy to cultivate. They are very easy to kill. For us, we are reservoir, but we can manage. They are soft. This one they are very easy to cultivate. That's what I mean. We used to depend on a very small piece of land growing cassava, beans, until we came to university. Now we can eat meat. But I used to get food from the gardens. You cannot eat beans until after harvest. So you can imagine where we came from. So I don't think I came from Makerere, I came from Fort Portal. So what else do I have to say about amber soils? They have good rootability. When you plant a crop, the roots can easily go through because they are porous, highly porous. You know, the roots follow the pores where there is water and air. Hope you remember that plant nutrition thing. Where there is water and air, the roots will follow so that the plant can grow. So they have good rootability and water storage capacity. And because of this, they support a number of agricultural crops. For example, if you come to Fort Portal here, we have a lot of sugarcane, tobacco, bananas. These are the crops we grow here. Sweet potatoes. Actually, for us, we are sweet potato eaters. But here in Busoga, they call it emboli. But for us here, we also eat potatoes. Cassava. You know, sweet potatoes they tolerate low pH levels. So because our pH is fixed here, potatoes don't mind, they can survive. I hope you know that plant nutrition thing. We grow a lot of tea because our soils are fertile and acidic. Vegetables, carrots. Green vegetables are plenty here. Wheat, we also grow wheat here. Orchard crops, forest trees, rice, they're all here. So that is the land use as far as these soils are concerned.